Hi everybody and welcome! Today's video is the first in a new format that's called paper analysis. Basically the idea that I want to experiment here is to try to explain influential research papers in AI audio and AI music. The aim of this series is to get you up to date with the current research literature in the field. At the same time, if you're a beginner, this will help you to understand how to read and obviously master these different research papers. So for the first video today, I'm going to talk about an interesting paper that covers automatic emotion recognition in music. So the whole point of starting this series is also to have a discussion with the community. And this discussion is going to happen on the Sound of AI Slack workspace. So I really suggest you to join the community there, where obviously you'll be able to ask for feedback and at the same time also to discuss ideas, discuss papers, and just brainstorm and share knowledge. Okay, so if you want to check this out, I'll just leave you a link in the description section below. But yeah, let's get started. So first of all, what I want to introduce here is the task of automatic music emotion recognition. Right, many of you probably are already familiar with this, but basically the task goes like this. So you have some music, for example, a song, and then you input that in a machine learning algorithm, and then you get back some kind of emotional prediction. So for example, this could be classification. So the model could tell you, yeah, this song is sad or this song is happy, or it could be some kind of a regression problem where you have as an output all the different possible moods. So for example, happy, sad, and then you get a value between 0 and 1 that tells you, yeah, this song is 0.2 happy and it's 0.5 sad, for example. Okay? So this is the basic idea behind automatic music emotion recognition. But you may be wondering, okay, so it's easy to say that you just input some songs into the network, but what does that mean? So what do you actually input? Well, that really depends on the type of machine learning algorithms that you use. Traditionally, I mean, in older literature, we would use all sorts of traditional machine learning algorithms like linear regression, logistic regression, or support vector machine. With the advent of the deep learning revolution, obviously also music emotion recognition has started to use deep neural networks. And so for deep neural networks, what we want to use is spectrograms, or basically spectrogram-like features. So what's a spectrogram? Well, with a spectrogram, we start from the raw audio and then we extracted it using the so-called short-time Fourier transform. And what that does, basically, it creates this kind of image, this graph, where you have the energy level of different frequency bands throughout the duration of the song. And the great thing about a spectrogram is that it has information about frequency, about temporal stuff, about the intensity, the energy of the sound, and it's a very nice snapshot of the sound itself. Now, I'm not going to get too much into the details of what a spectrogram is or how to pre-process that, because I'm just at the beginning of a whole new series, which is called Audio Processing for Machine Learning. So you should definitely check that out if you want to know more about this and you're not familiar. And I'll leave you a link up here so that you can just check the course overview of that new series. Okay, but now let's move on and understand that we currently have a problem in music emotion recognition. And the problem is that the moment we use a neural network, we're basically using a black box system. So we can't really explain while a neural network decides that, I don't know, like this song is happy or that song is sad. This is like a major problem, not just like in music emotion recognition, but across the board in deep learning, right? And for certain fields, this is like a crucial problem. So imagine a medical diagnosis, right? So you have a black box neural network that tells you that potentially you have like a disease, right? And well, while like it's very helpful to get like certain suggestions or predictions like this, but at the same time, medical professionals would like to know why this is the case. So what's the reasoning behind the network? And now with current systems, it's kind of like very difficult to understand how they reason, how they arrive at their predictions. And this is why we say that like deep neural nets are most of the time black boxes. We have the same problem in music emotion recognition. And basically the paper that I'm sharing today tries to account for and address that problem. Okay, and here we are finally at the paper. So the paper is called, two words, Explainable Music Emotion Recognition, the route via mid-level features. First of all, don't be scared about the title. So this happens all the time. So with research papers, they have like very, very big, scary titles. But then when you read through them still, I mean, there's a lot of complexity, but when you break it down, usually like you can access that and understand like their thinking. Now, this paper is by researchers at the University of Linz in Austria. So, and they are Chaudhary, Val, Haunschmidt, and Widmer. I hope I haven't mispronounced their names, but this is really a cool paper which came out last year in 2019 at the 20th iteration of the ISMIR conference. Okay, so what's the big idea here? Well, it's this mid-level features thing. So basically the big idea here is, okay, so we start from a song, so from raw audio, we extract some spectrogram from the song, but then we try to extract mid-level perceptual features, musical perceptual feature on top of the spectrogram. And by using these features, we're going to be able to explain the emotion predictions based on these mid-level features. Now, obviously, you may be wondering, but what are these mid-level perceptual features? And obviously, I'm going to respond to the question, or actually the researchers will respond to that question for you. So the mid-level perceptual features are features that, first of all, are musically meaningful. So they make sense musically. It's not just like very low-level audio features like a spectrogram where, well, it doesn't make any sense for us humans. These features instead can be explained musically. And they are recognizable by most listeners, meaning that you don't need to be a music expert or a music theory expert for recognizing them. Now, an example like of a musically meaningful feature that still it's not a mid-level perceptual feature could be like, for example, a cadence, right? So perfect cadence or certain chord progressions. And yeah, these are still like musically meaningful, but you have to be a music expert to understand what they are and to recognize them. Okay, this is a perfect cadence, this is a plagal cadence, but I mean, if you've never heard of music theory, you don't know what these things are. So mid-level perceptual features, on the other hand, are recognizable by most listeners. Now, let's take a look at what features, perceptual features the authors actually used in their research. So, and here you get a nice table where on the left side you have all the perceptual features that have been used in the paper. Then these are melodiousness, articulation, rhythmic stability, rhythmic complexity, dissonance, tonal stability, and modality in the sense of minorness. Now, I've copied in this table directly from the research paper, and I'll be using a lot of like their material, obviously, like for as a reference, like here in these explanations. Oh, by the way, so if you want to check out the actual paper, you'll find a link to it in the description section below. Okay, so here in this table, as I said, on the left-hand side you have the perceptual feature, and on the right-hand side you have questions that more or less explain the reasoning behind these features, right? So for example, for melodiousness, you basically respond to this question: to which except do you feel like singing along? So how melodious basically this segment of the song actually is, right? Okay, so these are the mid-level perceptual features, and as you see, these are things that can be understood by non-music experts, like dissonance. So basically, like, most people can tell you, yeah, this song is dissonant or it is not. Okay, so let's move on. So here, let's take a look at the actual data sets that the researchers have used for training their models. So obviously here we're going to need a couple of data sets. So one for the mid-level features and another one with emotion annotations. So for the mid-level features, they used 5,000 song snippets, which had scores between 0 and 10. They scaled that down by multiplying by 0.1 so that they had scores between 0 and 1. And the mid-level features, the annotations, were for 7 different classes. And these are like the mid-level musical perceptual features that we've just seen. Now, for the emotions dataset, they had 360 song snippets. And again, here the scores were between 0 and I believe 7.8 or something like that. And once again, they scaled that down, so they had it between 0 and 0.78. Now, the emotional features that they have in this dataset are 8. So we have like 4 discrete, let's call it this way, emotions. So happy, sad, tender, fearful, angry. And then we have some like continuous features like valence, which basically tells you how positive a certain mood is. So for example, happy is high valence, sad is low valence, and arousal, which is an indicator of the energy level of a mood. And then we have tension, right? And so all of these emotion features would get a score between 0 and 0.78 for the 360 songs. Now, an important thing to say is that these 360 songs are also featured in the mid-level features dataset. And so this is very important because we need to have both annotations, right? Both for the perceptual features and the emotional features, so that we can train like models like together. Okay, so this is like for the data set. Now, what kind of architectures have the authors built? And so here we have like 3 different architectures, right? And they are called with kind of like weird names. Like as you see here, A to E, A to mid to E, A to mid to E joint, right? It seems like that in the community, deep learning community, this is like a must. You have to give weird names to your deep learning models. Otherwise, like, that's not cool, I guess. Okay, but yeah, let's try to understand like each of these models and why they needed 3. So first of all of the 3 models share the same input, which is spectrograms. So they start from spectrograms. So the first one, it's called audio to emotion, A to E. And this is like the usual black box network that you get usually when you do music recognition the music recognition task, music emotion recognition task, sorry about that. So basically here, what this architecture does, it gets like a spectrogram, it has like a deep neural network, and then it makes predictions, but it's not explainable. It's a black box. And so you may be wondering, but why do we need this? Well, the assumption here is that this is going to be the architecture that's going to be like the most accurate, the most performant. And so we can use this as a baseline to see how well the architectures that are explainable can do compared with the baseline. In other words, we can use A to E for the cost of explainability, and the authors defined the cost of explainability as the difference in the quality of the predictions of the baseline, which is A to E, against the other explainable architectures. We'll see this in more detail in coming slides. Okay, so the second architecture that they built is a kind of like a two-step architecture. So it's called A to mid to E, which I guess stands for audio to mid-level features to emotion. But as you can see here, there are two blocks. So the first block is a deep neural net, and what it does, it is trained to predict mid-level features. Okay. So once you have this block that's trained, then there's another level here, which is called mid to E. And it's basically like a linear regression model, which gets as input the mid-level features, and it gives out emotion predictions as outputs. Okay, now there's a third architecture, which is called A to mid to E joint. So basically here we do audio to emotion, but going through the mid-level features. But all of that is, as the name suggests, like joint. So we only have one model that we train that's able to both predict mid-level features as well as emotions. And now we'll see why this is very important in a second. Okay, so here you have an idea of the main of the big picture of the different architectures that the researchers have built. And now a general thing that I want to say, like with these papers, usually it's a good idea to get like an understanding of the high level picture first and then go into the details, because sometimes like these papers are quite dense and you can just like lose yourself into the details. So you want to get like the bigger picture first and then dive into the nuances. And that's what we are doing now. So let's take a look at the architectural details. So now, first of all, the main neural network that the researchers use here is based on the VGG network, which is a famous type of architecture that uses a lot of like convolutional layers. And then the other main point here is that the main architecture, so this VGG style network, is shared across all models. All the three models basically use the same basic architecture, which is this guy here, right? So, and here, as you can see, we get as input a spectrogram, and specifically the dimension of the spectrogram is 149 by 313. And then that spectrogram gets input into this shared network, VGG style network, where we have a bunch of convolutional layers. And as you can see here, each layer has a convolution, then there's some batch normalization, and then there's a ReLU activation. Now, if you're not familiar with the details like of deep learning, I suggest you check out my other series that's complete now, and it's called Deep Learning for Audio in Python, and it's over here. So if you want just like to, if you are starting from scratch or you're not very familiar with the topic, I really suggest you to check that out. Okay, so as I said, so here we have the main architecture, but then we have differences once we get out like of this like VGG style network. So let's go one by one through all the models that the authors have built. The first one is again like the black box model, so A to E, audio to emotion. So basically here, like this is like quite straightforward. So we have like the VGG style network, and then after this adaptive average pooling layer, we have a fully connected layer with linear activations, which gets 256 like inputs, and then it outputs 8 units, right? And so in these 8 units are associated with the 8 different emotions that we want to predict, right? And the prediction here happens at a regression level. So basically, out of these 8 neurons, you are gonna get values which represent like the values that are associated with a specific emotion for that song. So here you'll have values like 0.1, 0.5, and that could mean this song is 0.1 happy and 0.5, I don't know, like valence or arousal, okay? So yeah, so here you have like this structure. Now let's move on to A to mid to E, which has like a little bit more complex structure. So as always, like we have a first part of this network like that's shared. So it's this VGG style network, but then these applies a fully connected linear layer, which has not 8 outputs, but 7 outputs. And so why is that the case? Well, that's the case because here we are training this first part of this two-stage algorithm to train mid-level features, to predict mid-level features. And so obviously we know that we have like 7 features, and so here we expect like 7 outputs, and the values, the predictions here will be for each of the mid-level features. So the researchers train the mid-level feature predictor first, and then they train a second model, which is a linear regression model that takes the 7 mid-level features as input, and it provides an output with 8 units, which once again are the 8 different emotions. Now, this layer, as I said, like is some kind of like is a linear model, which means it has only like linear activations. And you may be wondering, but why did they decide to have this type of layer? And that's the key to interpretability and explainability. I'm not going to get into the details of like why this is explainable now, but stay tuned for that because it's the key of this paper, really. Okay, let's move on to the third. Let's move on to the third architecture here. And so here, once again, you have like the usual VGG style network, and this is it basically. And then we have a mid-level layer. And so basically here, this is a fully connected layer, which outputs like 7 units. And the idea here is that you go down to like the mid-level features, and then you have another layer, which the researchers call the emotion layer, which is a fully connected like layer with linear activation, which gets like the 7 inputs, which are like the mid-level features, and then it outputs prediction for the different emotions. Now you may be wondering, but what's the difference between like this A to mid to E joined with A to mid to E? Well, don't they do like the same thing, going through like mid-level features and emotions? Well, more or less, yes, but the A to mid to E architecture does it like in 2 different steps. So you first train the mid-level features predictor and then the emotion predictor. Here you do everything together. And so how can you do that? Well, it's because they use some kind of combined loss. So they calculate the loss using the mid-level features, like at the mid-level feature layer, and then they calculate the loss for the emotions at the emotion layer, and then they combine that and use that combined loss to optimize the whole network so that hopefully it will learn representations and learn to predict both mid-level features with this layer, the mid-level feature layer, and then emotions with the emotion layer. Okay, nice. So now we have like an idea of like the 3 different architectures. So what the researchers did at this point after building the models was just like to experiment with them. So they run training sessions with this, and they just like looked at the results. Now, if you want to know the details about like the hyperparameters that they used and the training parameters and all of that, I refer you back to the paper for that. We'll just go straight into the experimental results. Okay, so here you see a table from the paper, so where you see basically the different models here and the and metric here that tells you like how good like these models performed. And now the metric here is the Pearson correlation coefficient. And basically like here, they just like try to correlate the results, the predictions with the annotations. Okay, so the first row here is for the base level, right? It's for the audio to emotion model, and it has an average score of 0.76. Okay, and now if we go down to the A to mid to E model, we see that the average score goes down to 0.71. So it's still doing like quite well, but as the researchers were expecting, it's a little bit like less performant. Now, however, if we go down to the results for the A to mid to E joint, so the combined model, you'll see that the result is 0.75 over here, which is basically almost like identical to the baseline model. So with all of this, what we see is that the cost of explainability is quite low. And specifically for the A to mid to E model, it is 0.05, right? Whereas for the A to mid to E joint is 0.001, right? So, I mean, yes, of course, we lost a little bit of performance, but at the same time, we gained in explainability, which is the whole point of this paper. But now you may be wondering, but how can we explain the results, right? Because I've been bragging about explainability all the time here. So let's take a look at how we can explain the reasoning behind the network. Okay, and so for that, we can use weights, right? Not this type of weights, another type of weights. Okay, so let's understand what that is. Okay, so here I'll just like take as an example the joint, the architecture of the joint network, and I'll take a look at the weights of the linear layer. So here we have the mid-level layer, and then we have like the emotional layer. So the mid-level layer has 7 neurons, 7 units. So each unit we can think is associated with a different mid-level perceptual feature. So the first one could be dissonance, the second articulation, and so on until you get like all the 7 of them. And then same thing with the emotional layer, which however has 8 neurons. So the first one could be associated with happy, the second with sad, and you can continue and put it in like all the different 8 emotional features, but I won't do that. Okay, so what happens here is that we obviously, like when we connect, this is going to be like a fully connected layer, right? So all the neurons from the mid-level layer are going to be connected to each of the neurons in the emotion layer. Now here I've only drawn the connection between the input neurons with the happy output neuron in the emotional layer, just like not to make like the whole drawing here like a complete mess, but you get the idea, right? Okay, and the mathematics that we have behind here is this one. And it's kind of like very straightforward. So in order to get the value for happy, so what we do is a linear combination of the weights between like each input neuron and the happy output neuron multiplied by the value of the input neurons. So the first thing that we do here is like the weight between dissonance and happy, and we multiply that by dissonance. Then we add the multiplication between the weight between articulation and happy, and multiplying by the value of articulation. And then we have this B value here, which is just like a bias value. Okay, so here, just like to give you an idea, like if you're not familiar with fully connected layers, like so this connection, this weight here is for this first connection here. It's basically like the how much like present or how much strong dissonance of an influence dissonance has on happy, right? So basically the idea here is that the higher the weight, and the higher obviously the influence that a certain input feature is going to have, in this case on happy, or like in this case, the higher WDH, the higher the impact that dissonance is going to have on happy. So if we look at the features, at all the features for all the connections between the mid-level perceptual features and the emotional features, then we get an idea of potentially like the influence that the mid-level features have on the emotional features, right? Okay, and this is a measure that will tell us like how the model understands the correlation between mid-level features and the emotional features. So let's bring like this very cool heat map that was like obviously like published by the researchers. So here like on the rows, you have like all the mid-level features like minorness, tonal stability, dissonance, and on the columns you have like this valence energy, all the different emotional features. And these values are basically the weights between like those two, between like the mid-level features and the relative emotional features. Okay, and so here we can see, for example, that the weight between dissonance and fear is quite high. It's 0.57. And this makes sense, right? Because, for example, when we watch a horror movie with a horror soundtrack, we usually get a lot of dissonances and we get scared of that, right? And so basically like this type of like explanation of the model, of the reasoning of the model, is the equivalent of like what we would do as humans, like asking ourselves, okay, but why is that song so tense? And you may be thinking, yeah, that's tense because I don't know, like it's very complex rhythmically and it has a lot of like minorness. There's a lot of like minor chords in there. And so basically like what we are doing like with these weights is kind of like getting like that gist, that idea. Okay, let's move on to another example. So now there's a quite high influence, for example, of melodiousness on tenderness, right? And this makes sense because like if you can sing along with a song, it means that probably it's chill out and it's tender. But now if we take a look at this last point that I want to show you, like there's a kind of like inverse influence between dissonance and happy. And again, this makes sense because happy music usually doesn't have like many dissonances. Okay, so here you start to see like explainability of the network at the level of the model. But what about a specific explainability for a specific song, right? Can we explain why a network decided that a song has like certain moods? Yes, we can do that. And the researchers suggest that we use the effects of mid-level features on emotion. Now, effects, the way they define effects is basically like the multiplication in the linear combination of the linear layer between the weight and the actual value of the mid-level feature. Okay, so it's this combined value. Obviously, like for example, in this case, dissonance is going to be different for each song, right? The weight is going to remain the same, but dissonance is going to change, right? So if I'm listening to some very weird like Genesis or Gentle Giant song, probably there's a lot of dissonance. But if I'm listening to some folk song, probably dissonance is quite low, right? Okay, so this is, for example, the effect for dissonance. This is the effect for articulation, right? Okay, so now the question is, so how do we visualize like the effect of different mid-level features on emotion? And here the researchers came out with this wonderful box graph. So here in each of these like boxes over here, basically you have the effects that the mid-level features have on, for example, energy here, on tension, or on anger. And so let's take like this one, for example. This is the effect that minorness has on tension. Right, and here, like in this box, you get like the distribution, and here you have like actual points, so or dots. So, for example, you have the red dot or the blue dot, and these are actual songs. And so the researchers have analyzed a couple of songs, and they came out and they put it like in here, so that you can have like an idea of how much minorness had an influence on tension in the case of this red dot, this song, and this other blue song. That's cool. Right, and so this way we can easily explain why a song has certain emotions based on mid-level features that all human beings who listen to music are capable of like understanding and realizing. Now, research is only as good as, well, not really, but I mean, like in engineering, you would say that some piece of research is only as good as like its application. So what are like some possible applications here for this research? So first of all, by using this method, we could suggest explanations in music recommender systems. So sometimes you get recommendations, music recommendations from recommender systems, and these don't come with like any explanation. And that's really a problem because we want explanation. So we want for the system to be capable of saying, yeah, hey, I've suggested you like this song because of A, B, C. And with this system, we can definitely do that in the emotion realm. Then a great application would also be for music search engines, right? Now, with a system like this, not only you can search for music in certain moods, but then you can say, okay, give me music with this mood, which is like high tension, but at the same time, which has low dissonance, for example, right? So you can create more refined searches. And finally, you can use like the same like basic idea for creating playlists, right? So you may want to create a playlist which is in a mood, right? Say, for example, happy mood, but still you want to have like the liberty of choosing, yeah, I want songs that are happy, but I want songs that are rhythmically complex at the same time. And so with something like this, you can do that. Good. Okay, so what have we learned from this analysis of this like great paper? So first of all, it's possible to train effective non-black box models for music emotion recognition, right? And this is like extremely interesting in itself. But the cool thing is that probably, given like this is possible for this particular task, perhaps we can try to extend like explainability to other audio classification tasks and even further than that. And then the other main thing that we've learned is that the cost of explainability is fairly low, at least like in our example. So yes, we lost a little bit like in performance, in quality of the predictions, but that wasn't really like that much. So yeah, we lose a little bit of performance, but at the same time, we gain quite a lot on explainability. Well, we actually gain everything on explainability. Cool. Okay. So that's really like it for today. I hope like you really enjoyed like this explanation of this cool paper. And once again, I want to invite you to join the discussion on the Sound of AI Slack channel. So there you'll find like this cool community of people who are just like sharing knowledge about all things AI audio and AI music. And we'll just like continue the discussion regarding like this paper and future papers that I'll review. Okay, so I'll leave you the sign up link to the Sound of AI community in the description below. And if you've liked the video, yeah, please like leave a like. And if you haven't subscribed yet, consider subscribing. And I guess I'll see you next time. Cheers.